Hi class. Linear algebra. Okay. Let's talk about something that we learned a while ago. Let's recall corollary 8 that says if we look at the equation given by ax is equal to the vector b, it has a unique solution if and only if a is non-singular. We learnt this corollary long before we knew what a determinant was, before we knew what linear independence was, etc. So let's revisit and reinterpret this result based on what we know now. All right, so ax is equal to b as an equation has a solution if and only if b is in what we now know to be the column space of A. Just to lay out the details of this, say A is equal to A11 through A1n, AN1, ANN as usual. These columns being the vectors, A1 through AN, and B is equal to C1 A1 plus ... CN AN, as in B is some linear combination of the columns of A. This can be rewritten as the matrix A times the column vectors C1 through Cn, and this is the solution. All right, that's what it means for ax is equal to b to have a solution. Let's think about it in terms of a quick example. So if I've got 1, 0, 0, 0, 1, 0, 1, 1, 0 as three vectors, this being the matrix A, and we've got the vector 0, 0, 1 being the matrix B, the vector B. This is going to have a solution if and only if B is in the column space of A. And we can actually do a quick sketch of this column space. Well, it actually is this plane, the xy plane, because here's A1, here's A2, and here's A3, all in the blue plane, and the vector that we're interested in, B0, 0, 1, is in this direction. So B is not in the column space of A, so this equation has no solution. All right, let's continue to revisit and reinterpret. Ax is equal to b has a unique solution, as in corollary B, if and only if the columns of A are linearly independent. This is coming from theorem 23, where we know that A being non-singular is equivalent to the columns being linearly independent, i.e., there is only one possible set of values for the CIs when B is going to be expressed as a linear combination of the columns of A. Let's gather these ideas to what we've been working towards, the idea of the basis. Definition. Say V1 through Vn are vectors in a vector space V. They form a basis for V if and only if these two things happen. Number one, V1 through Vn are linearly independent. And two, v1 through vn form a spanning set for v. Let's do a quick example. Example, 1, 1, 1, 1, 1, 0, 1, 0, 0. We're going to call these vectors v1, v2, and v3. From a previous lesson, we know that these span R3. As in, every vector in R3 can be expressed as a linear combination of v1, v2, and v3. Knowing what we know now, we know that we can also bring in the idea of the determinant to this discussion. So if we took a matrix where these vectors form the columns and I found the determinant, well, because it's triangular, the determinant is just the product of the diagonal entries. And this, my friends, is not 0. And the determinant being not 0 means that the columns are linearly independent. Therefore, v1, v2, and v3 form a basis for R3. They are linearly independent and they span all of R3. Here's a question you might have. Why is this desirable? Why is having a basis a nice thing? Well, let's take a closer look. Not only can we express every element of the vector space as a linear combination of v1, v2, and v3, but also by corollary 8, this linear combination is unique. As in, for v in R3, there exists C1, C2, and C3 so that v is equal to C1, v1 plus C2, v2 plus C3, v3. Let's add our little vector symbols here. And there is one answer. One possible such expression. There's only one set of values that will work. Compare a more chaotic situation. 1, 2, 4, 2, 1, 3, 4, negative 1, 1. A1 vector, A2 vector, and A3 vector. Where, okay, as we would expect, we can express the 0 vector as a linear combination of A1, A2, and A3, where the coefficients are all 0. That makes sense. But something that's disturbing that we've explored a little bit before is that you can also do this. I don't like this. This makes me upset. We like bases, where the expression is unique. There's only one way to express things. So note, A1, A2, and A3 are not linearly independent. And that's why this happens. Let's do an example. Let's do an exercise. Show that the vectors 1, 3 and 2, 4 form a basis for R3. For R2. I.e., there's two things that you need to show. A, show that every vector in R2 can be expressed as a linear combination of these vectors. So say AB is in R2. AB can be expressed as C1 times 1, 3, plus C2 times 2, 4. And I want you to find C1 and C2 in this generic setup. B, that'll show that it spans, and B, show that 1, 3, and 2, 4 are linearly independent. Showing A and B will show that these two vectors form a basis for R2. Okay. In looking at that last exercise, one might think that part A was a little bit annoying, and it is. So a question that you might have is there an easier way to do an exercise like this? Like the above, without doing A. As in, without manually checking that you can express literally any vector in terms of the other vectors. The answer is yes. And for us to understand this answer, we're actually going to have to go through and learn some properties about bases, which is for our next lesson. But in order to get there, we do need to introduce one more idea. Let's talk about dimension. Say I is an index set. Definition. Say you've got some collection. This collection of vectors is a basis of a vector space V. As in the VI's are vectors in the vector space. The VI's span V, and the VI's themselves are linearly independent to each other. Then the dimension of V is denoted dim of V and is the size of your index set. You can also say that if I is less than infinity, we say that V is finite dimensional. V will be a finite dimensional vector space. And if the size of I is infinite, we say V is infinite dimensional. One exception, as it usually is the trivial vector space. The dimension of the trivial vector space is by convention given by 0. Let's do some examples. Example. I'm claiming that the dimension of R3 is equal to 3. This might seem obvious. Let's connect it precisely to the ideas that we've been using. It is three-dimensional because it has a basis 1, 0, 0, 0, 1, 0, and 0, 0, 1. These span all of R3 and are linearly independent to each other. They form a basis for R3, and there are 1, 2, 3 of them. Therefore, dimension of R3 is 3. Example. Remember this vector space? This is the vector space of all polynomials of degree less than n. So the elements look like this. Where these coefficients are real numbers. Okay. Just by looking at this, we can see that this is spanned by 1x all the way up to x to the n minus 1. Every element in the vector space can be expressed as a linear combination of these vectors. You can show, using the Wronskian, that they are linearly independent. In fact, we had you do this last class. And so Pn is an n-dimensional vector space. Because it has a basis of size n, these n vectors. All right, that's two examples of finite dimensional vector spaces. Let's look at P, which I'm going to call, well, I'm using that to denote the vector space of all polynomials in X with real coefficients. Okay. I'm going to claim that P is an infinite dimensional vector space with basis 1, x, x squared, etc. We'll just discuss the idea. The idea is that 1, x, x squared, xn is linearly independent. Sure, but it's linearly independent for all possible n. And P contains for all n and is spanned by this full collection. All polynomials can be written in terms of powers of x and a real number. Therefore, we can conclude, or at least have the idea, that P is infinite dimensional as a vector space. Okay, we've learned what a basis is, and we've learned what the dimension of a vector space is. I expect there to be some lingering questions. How do I check that V1 through Vn forms a basis for a vector space V without actually manually checking, without checking directly, that every vector in V can be expressed as a linear combination of V1 through Vn. This will become clear, hopefully by next lesson, when we explore the properties of bases. So think on this until then. See you next time.